Video 8 Part 1, Production Script, Component, ESP-16, Steering Column, Resolution and Geometric Optimization. Welcome back to the laboratory. In our previous segment, we established a severe engineering conflict within the ESP-16 steering assembly. Switching from grade 5 titanium to 7000 series aluminium achieved a significant mass reduction, but compromised the structural margin against localized plastic buckling and high-frequency fatigue. Today, we review the definitive engineering resolution to this multi-axial stress dilemma. The structural resolution, geometric compensation. To resolve the compliance deficit of the aluminium sleeve without reverting to the mass of a titanium architecture, the engineering team rejected a simple wall thickness increase. Instead, the solution relied on geometric optimization of the cross-section. By increasing the outer diameter exclusively at the high-stress boundary zones, the area moment of inertia was strategically elevated. This precise modification effectively redistributed the secondary bending moments induced during aggressive curb riding, ensuring the structural stress remains safely below the material's yield strength. Calibration of the energy dissipation regime. The critical challenge was protecting the safety module's core function, ensuring the calibrated shear pins reach their 10 kN failure threshold before the surrounding sleeve undergoes nonlinear deformation. Through finite element analysis, the coupling interface was redesigned with a dual-stage constraint. Under standard racing frequencies at 500 Hz, an elastomeric damping layer isolates the cumulative fatigue damage. However, under impact loading, the optimized geometry guarantees a purely axial force transmission. This forces the kinetic energy to dissipate cleanly through the shear pins, executing a flawless telescopic collapse. The Engineering Whiteboard Challenge. Now, let us open the laboratory whiteboard to evaluate your department's analytical capabilities. Look at the technical index reference at the end of this broadcast and address the challenge that matches your expertise. Student level challenge, focus, structural mechanics and bending. Using the cross-section model in image 1, demonstrate mathematically how increasing the outer diameter of the aluminium sleeve modifies the area moment of inertia. Calculate the percentage gain in pure bending resistance compared to the original thin-walled design. Is this geometric shift alone sufficient to keep the acting stress below the yield strength of the 7000 series alloy? Professional level challenge, focus, linear dynamics and cumulative fatigue. The ESP-16 assembly is subjected to continuous 500 Hz excitation from track inputs. Based on the material's SN curve and using the Palmgren minor linear damage rule, determine the operational cycle limit before micro-cracking initiates at the stress concentration zones. What specific elastomeric interface properties would you select to isolate this frequency without compromising torsional stiffness? Master level challenge, focus, nonlinear dynamics and continuum mechanics. Analyze the destructive transition state using the finite element analysis model in image 2. When frontal impact introduces a combined bending moment and multi-axial compression force, the aluminium sleeve enters a nonlinear strain regime. Formulate the differential energy dissipation equations through the plastic volume integral to prove the housing will not suffer localized plastic buckling before the shear pins cleanly reach their 10 kN pure shear limit. Prove that the collapse vector remains strictly axial. Submit your structural equations and analytical arguments in the comments section below. The most rigorous, engineering-backed solutions will be pulled directly onto the laboratory whiteboard for deep dive evaluation in our next segment. All full-scale reference diagrams, material graphs, and mathematical models are provided as a complete index suite at the end of this video for your detailed verification. Make sure to subscribe so you do not miss the engineering outcome in Video 8 Part 2. I will see you in the laboratory.